Giving the talk today for the deal.II project will be Wolfgang Bangerth. He's a professor of mathematics and, by courtesy, geosciences at Colorado State University, and he was previously a professor at Texas A&M University and a postdoc at the University of Texas at Austin. He received his PhD in mathematics from Heidelberg University in 2002. His research is on the development of widely usable finite element methods, their algorithmic implementation in open source software, and applications of computational methods throughout the sciences and engineering. His passion is to utilize mathematical and computational ideas in areas outside of mathematics. In pursuit of this, he's collaborated with scientists with affiliations from departments in astrophysics to zoology, and his publications are in journals that cover as many fields. He has further received his university's 2024 Interdisciplinary Scholarship Award. A concrete incarnation of his desire to make his results widely available is the deal.II project, of which he is one of the founders and continues to be a principal developer. deal.II is a widely used open source software library that provides tools for the finite element solution of partial differential equations. For the creation of this software, he has previously co-received SIAM's James H. Wilkinson Prize for numerical software in 2007.
Well, this is quite the honor, of course, to be up here and to be speaking for my co-authors. There's 14 of us, 9 in one place, which does not happen very often. So I really appreciate this, Carol. I appreciate the whole SIAM community for making this possible. We write software for a community, and this is our community. It's very nice to be standing up here. Let me see if I can connect this real quick. All right, so the deal.II project is run by a collective, and you've seen all of these folks here. We're 14 of those, and what I want to talk to you about for the next 20 or 25 minutes is how does a project like this work? What is part of it? I recognize that all of us use software in one way or the other. Very few of us are involved in actually building software at this scale. And so my task is to walk you through this process a little bit. So the premise of all of this is that if you look at the progress this community, the SIAM community, has made over the last 20, 30, 40 years in actually solving problems, it's huge. I mean, I've been coming to SIAM CS&E conferences for 22 years, since 2003. And it is very noticeable what we can do today and what we could do 22 years ago. The concrete incarnation of all of the methods that we develop is fundamentally software. That at the end of the day, when we think about solving a problem, we have to implement it, right? It has to be in software so that we can produce concrete numbers for what we want to do. And if you think about the sort of things that we do want to do, it should be, it should have a complex model, right? You look at Omar's models of earthquake propagation. There's concrete topography in there. There's the material description in there. There's complex constitutive laws. There's solvers and preconditioners and matrix and so on and so forth. And all of this, of course, should work on the best methods that we have today, and it should work highly parallel. And unless, of course, you have a research group as big as Omar's, you cannot possibly implement these sort of solvers today from scratch. It's just not feasible, right? That the software that we use for realistic problems today would have millions of lines of code, and it would take many decades to build something like this. So a good number in the industry is that a full-time programmer can produce about 20,000 lines of code per year. So software that has millions of lines of code requires a very, very substantial human investment to build. So how do you make this possible? As a community, as the applied math community, over the last I don't know, 50, 60 years, we have built software packages. There were packages like Blais and LAPAC, and before that, IcePack. So collections of tools that we have widely used in our community. And that started out with linear algebra packages and maybe quadrature packages, the sort of things that you can fit into a few hundred lines of Fortran. But today, these packages encompass basically everything that can be sort of packaged into something. So there's linear algebra packages like PETSI and Trilinos for sparse linear algebra. There are eigenvalue solvers. There's sundials, which got this prize 2023, 2 years ago, that solves ODEs. There's packages for optimization, and then there's a number of packages like Phoenix or MFEM, LibMesh for PDE solvers. And deal.II sits very squarely in this field of packages that encapsulate the different building blocks that people can then build their own software on. And in particular, deal.II is a finite element package. So let me walk you through a little bit what is in deal.II. So concretely, the premise is like for many of these other packages, the tried and true approach that we provide building blocks. We do not provide an application that solves a concrete thing, but we provide building blocks that you can then write whatever it is that you want on top of. So in the case of deal.II, what we want to achieve is that we can solve complex PDEs in a variety of areas. It should be discipline independent, so it is not a mechanical engineering package, it is not a fluid mechanics package, it provides tools for all of these sort of things. We set out in 1997 when we started this as a tool that was intended to support adaptive finite elements. So we wanted to solve problems on meshes that can be locally refined and dynamically changed. Over the years, we have acquired the ability to solve problems on hundreds of thousands of processors, but at the same time, we recognize that much of the research that we do today continues to be on individual workstations or laptops, and so that is certainly something that we still do want to support as well. The sort of things that it has in concrete terms is it provides adaptive meshes in 1D, 2D, and 3D. These meshes can be quads or hexes, but they can also be triangles and tetrahedra or mixed meshes. There's a whole zoo of elements. If you heard of it, it's probably in deal.II. It can be low and high order. You can have operators that are matrix-free and matrix-based. There's support for multigrid of various kinds. There's multiphysics support in there. And like Carol already said, there's interfaces to basically every package you can think about. I think I list 6 or 7 here, but the list is about 30 deep. It is parallelized with SIMD, with threads, with tasks, with MPIs. It runs on GPUs. It is also a teaching tool for us. So if you think about the finite element method, there is a lot of theoretical background that students have to learn to understand how this actually works. And we have built a very large collection of teaching tools that introduce the finite element method and sort of the ideas behind this. So there's on the order of 90 tutorial programs that solve a variety of problems, from simple Laplace problems to medium-sized problems with maybe a few thousands of lines of code. The goal of this is we, of course, want to teach deal.II, but we also want to teach numerical methods. That has turned out to be a very interesting side aspect of a library like this, that it is used in teaching not just among the principal developers or maybe the people who use it for their own research, but it is a teaching tool also in courses taught around the world. Most of the codes that people build, I should say, built on these tutorial programs as a starting point. For teaching as well, we have recorded a number of lectures, about 75, that are hosted on YouTube, or if you don't have access to YouTube, then on Bilibili. That's a Chinese equivalent of this. that teach also finite element methods and numerical methods in general that have proven to be surprisingly well watched around the world, about 250,000 views so far. In numbers, so I told you it is a library. It has about 1.9 million lines of C++ today. We try to make this modern C++, so one of the things that we do is we consider how to evolve the software system with the standards of the C++ programming language. It has about 14,000 tests that we run on quite a number of machines with every change that anybody proposes. It has more than 10,000 pages of documentation. It runs on Mac, Windows, and Linux through a portable build system. It runs on laptops. It also runs on the biggest supercomputers. And in many cases, it is fairly easy to install by just saying apt install deal.II, for example. So it is packaged in the packaging system of many of the Linux systems. And if you can use it on Linux, you can also use it on Windows, for example, through the Windows Linux subsystem. So having told you what it is that we want to provide, one of the questions, of course, is, will they actually use it? And I think one of the realizations of software is that just because you build it does not mean that actually anybody uses it. So I would like to talk a little bit about what is it actually used for. And so a few years ago, I made an exercise to go through all of the publications during 1 year to see what people built with deal.II. And it is quite a long list. So there were applications in the biomedical field, for example, at the top left. Then there were a whole bunch of applications in fluid dynamics. Some in fundamental physics. At the bottom left, numerical methods research. This is where we set out. I have a math PhD. I wanted to really just do math research, numerical methods research. At the top right, there's a whole bunch of applications in solid mechanics. There's some electronics and photonics. There's some people who use it for financial modeling. There's some people who use it in the geosciences. And I could make this sort of list for every year that we have collected publications of people using deal.II. There's also a number of fairly sizable codes that were written in different fields that built on deal.II. So one that I'm involved in is called Aspect. That is the advanced solver for planetary evolution, convection, and tectonics that has more than 250,000 lines of code on its own. There is a code, OpenFCST, for fuel cell simulations. There's a code called DFT-FE for density functional theory that got the Gordon Bell Prize this year or a couple years ago. There's a code called LETE for fluid dynamics. There are many, many more that I could list that themselves are very sizable software packages that solve a concrete problem with the help of deal.II and the interfaces that we have to other software packages. And just to give you a few concrete examples, so people have solved fluid structure interactions in vascular modeling. So this is a model that takes into account the fiber structure of vessels, how they bend and expand and shrink under the pressure of the pumping heart. There is models like this that come out of zoology where people want to model how do different parts of organisms grow. There are models that describe electronics and photonics and sort of very small scales and how you can homogenize those. There are models out of physiology. So this is a model that simulates the mechanics and the muscular response of the upper airways. There are models that describe the electrophysiology. So it's a coupled electrical, mechanical, fluid model of the heart and how that behaves. There are models that describe fracture in solids. And there are models that describe convection in the Earth interior, for example. So this covers essentially the entire breadth of the sciences, right? There is apparently not a thing that you want to simulate with finite elements in the sciences that you could not do with deal.II if you wanted to. So if you look at what these codes use, the list is quite long. So they often use higher order time-stepping methods. They often use higher order finite elements. They often use fully adaptive, changing 3D meshes that change from one time step to the next. They use methods like Newton's method for the nonlinearity. They use algebraic and geometric multigrid to precondition the elliptic parts in block-structured preconditioners. They use parallelization in many different ways. And if you think about building a code like this from scratch, you will probably realize that that is not reasonable, right? That is the sort of thing that would take a whole research group a decade to build. That we cannot do work if this is what we want to do. But this is what we want to do, because this is what is necessary to really solve the complicated problems that we do want to attack as applied mathematicians. So if you step back and you look at a list this long, you'll realize that if we do build unpackaged software, we can achieve things that would not otherwise be achievable. And in particular, if you think about how we often pride ourselves that mathematics is the universal language of all of the sciences, this is the way in which it actually works, right? That it is not enough for us to write a paper that says, yeah, you could use this method if you were an applied scientist wanting to solve an applied problem. But we actually have to provide the method in terms of software. And packages like deal.II or Sundials or PETSI or any of the other ones that I have referenced do exactly this. They encode the mathematical knowledge and make it available to all of the other scientists and sciences as the universal language that we speak. So I mentioned what it is that we provide and what it is that people do with it. And I want to walk you for the last few minutes, at least briefly, through the process. Like, what does it involve to build a package like this? And one of the realizations that perhaps is underappreciated is that building software is not about being a good programmer. Being a good programmer is probably a good precondition. You have to be able to write software. You have to know the programming language. You have to understand algorithms. But at the end of the day, it's about people. That every project of a significant size is about people, right? We're 14 here. There are hundreds of people out there that use deal.II that we want to educate and teach and help them to use it, for example. And so leadership in projects like this involves dealing with people. So let me tell you just a small piece of the people that are involved. So over the years, since 1997, about 370 people have contributed to deal.II, have contributed substantial pieces of code. These contributions come from all continents. Antarctica was missing, and we've fixed that this year. So all 7 continents are represented among the places where contributions come from. These contributors come from academia, from the national labs, and from industry. They come from the undergraduate years to people who are near retirement. There are 13 principal developers right now. They come from 5 different countries. Actually, they live in 5 different countries. They come from more. They are also in academia, in the national labs, and in industry. And among the principal developers, there are mathematicians, there are geoscientists, there are material scientists, there are nuclear engineers, chemical engineers, and civil engineers. So it's quite a lot of different backgrounds that contribute to packages of this size. We put out about 1 release every year, and for each release, about 40 people contribute. The way this process works is we use GitHub, like most projects today, and we have approximately 10 pull requests every day that get merged. So I count this as the joys of running a project like this. Here's another piece of joy. We We collect the number of publications, we collect a list of publications that use deal.II, not just cite deal.II, but actually use deal.II. And I like the shape of this graph. I think everybody would. It adds about 200 and some publications per year these days. That's one paper every 1.5 days that is published on deal.II that we know of. There's probably more that we don't know of. There's also things like this. So many years ago, we always said, triangles are never going to happen. deal.II only uses quadrilaterals in hexahedra. And then somebody, Peter, came along and said, I have an idea for how to make this work. And he implemented a whole bunch of code. And that worked so well that everybody helped out with it. It was a community effort to actually convert very large pieces of the library to use, or to be able to use triangles in tetrahedra. And so these are sort of the miraculous things that can happen if you work in big organizations where somebody shows up and has a great idea and the energy to do it, and it's just a miracle. It just works. So I really enjoy these sort of moments, right, where stuff actually happens. And I could mention other things, the matrix-free operators, the interfaces to sundials, many other packages, support for automatic differentiation. One person shows up, has a great idea and the energy to do it, and then everybody contributes to it. It makes it workable through the entire library. What's also a joy is to see how many organizations have actually funded development of deal.II. So there's the National Science Foundation, DOE and DOD, the Department of Homeland Security in the United States. But then there's agencies in Germany, in the European Union, in Poland, in Italy, in Saudi Arabia. It's really nice. This is just the support that the principal developers have gotten. There's many, many projects in many countries where people have asked for support to implement a concrete solver in a concrete, for a concrete problem, and parts of that were ultimately put back into deal.II. There's also things that you have to deal with that are perhaps less glamorous. So in deal.II, there's a mailing list, a forum, that receives about 1,500 posts per year, between 1,500 and 2,000. They need to be answered. That takes a lot of time. And not all of these questions on the forum are of the kind where somebody says, I know you're busy, I would like some help. Few of us are actually paid for this thing. And so there is a real drain on energy to keep this up day after day after day. The same is true for the number of patches that we receive, right? There's on the order of 3,000 pull requests per year that have to be reviewed. Oftentimes, they go through multiple iterations. All of us are involved in this, but it is a lot of work to do this. Much of this work is unseen. It is oftentimes unappreciated. It is not something that you can easily put on your annual report to your department head, for example. It is not something that makes for a good line item on your application for tenure and promotion. So there is a lot of work that is less visible than getting an award like this, right? So there is an issue with maintainer burnout, and I think that is something that every open source project knows one way or the other. There's also the following issue. I have tenure. I can afford to work on these sort of things. Much of the work is done by people who are on temporary positions, graduate students, postdocs that contribute pieces of code, make available their time and their energy to contribute to a project like this. Because people are on temporary employment, there's also a lot of turnover, and so we spend a lot of time onboarding people, teaching people how to contribute to open source projects. And then you will have seen this from us standing here on the stage. our community is not very diverse. The deal.II community is not diverse. The 370 contributors that contributed code to deal.II is not very diverse. And I think this is generally true for the community that develops scientific software. So this is something that I think perhaps this is not politically expedient anymore these days, but we ought to continue to work on this. We lose out on a lot of contributions and ideas from people who have not been included in this community in the past, and then I think we should continue to work on doing a better job about this. Between the perils and the joys, at least for me, the overwhelming feeling is still, it is a great joy to work on this. It is a project that apparently to a lot of people is quite useful. It brings people together from different communities and has allowed us to build, at least the 13, 14 of us, to build good careers on this. It is clearly also appreciated by SIAM and by this community, and we're very thankful for this. I would like to end this talk on a personal note, or maybe two. The first commits to deal.II were in 1997. This is me in 1997 and 28 years later. Very few of us get to work for 28 years on the same project that works well. I'm immensely grateful personally to have been able to work on this and to work with great friends and colleagues, people who really do count as my friends today. And I think as a collective, as all of these developers who have worked many years, in parts decades, on this project, we're really grateful for this community, right? Writing deal.II is not a project for us, it's a project for the community. And to see the support in the form of the publications, this prize, of this community, this is what really motivates. We really appreciate that. With this, thank you very much. Thank you.
Are there any questions for Wolfgang?
Yes. Sorry. Maybe I missed it, but why is it called deal.II?
It's a fair question. In the lab where I was a graduate student with my colleague and friend Guido Kanschat, there used to be a library that is called DEAL, the Differential Equations Analysis Library. And it was time to be replaced by something different, and we called it deal.II.
I just wanted to say bravo.
Well, thank you very much.
I think on that note, we will end today, but I want to say congratulations again to the deal.II team and to Aaron and Omar as well. So congratulations.